Let us consider an equilateral triangle with a side length equal to n. Let us also consider the equilateral triangles of side length equal to 1, which are inside this triangle. Observe that these triangles are divided between the upward unit triangles and the downward unit triangles. Now, let us cut out n upward unit triangles. With the last condition satisfies, we say that we have a Holey triangle. A diamond is a shape which consists of upward and downward unit triangles. These triangles can be composed one above the other, or one beside the other. We say that our Holey triangle has a tiling if it can be tiled by diamonds. For example, let us show how to tile the Holey triangle in the illustration. Prove that a Holey triangle T can be tiled with diamonds if and only if the following condition holds. Every upward equilateral triangle of side length k in T contains at most k holes, for k between 1 and n. For example, let us look at the triangle in the illustration of side length 5. Let us cut out 5 upward unit triangles to obtain a Holey triangle. In the emphasized equilateral triangle of size length 4 we have 5 omitted triangles. Hence, by our main assertion, our Holey triangle cannot be tiled. Let us verify that this is indeed the case. As we can see, the bottom line is now detached from the rest of our Holey triangle. Thus it must be tiled independently. Let us look at the rightmost unit upward triangle in this row. The only way to tile it is by using the diamond, as can be seen in the upper right corner. We can continue in this way and make the same argument for the new rightmost unit upward triangle. In the end, we are left with the unit upward triangle in the illustration which cannot be tiled. Hence, in conclusion, our Holey triangle cannot be tiled. Let us prove our main assertion for the general case of an equilateral triangle of size length n. First, we cut out n unit upward triangles to obtain a Holey triangle. The necessity of our main assertion will be proven first. We assume that our Holey triangle has a tiling. Now, we consider an arbitrary equilateral triangle T of size length k. We need to show that this triangle is missing at most k unit upward triangles. To prove this, first, let us use our assumption that our Holey triangle has a tiling. Let us focus on the diamonds which cover at least one triangle in T, and denote this figure by R. Our main observation is that the boundary of T consists only of upward unit triangles. Hence, if T has H holes, then R is a triangle of size K with also H holes, and possibly some unit downward triangles sticking out. Thus, there are exactly K square plus K divided by 2 minus H unit upward triangles in R, and exactly K square minus K divided by 2 downward unit triangles in R, not counting those sticking out. On the other hand, each diamond covers one upward and one downward unit triangle. Hence, we have the following inequality, which implies that H is smaller or equal to K, as needed. Let us now prove the sufficiency part of our main assertion. Again, we start with a Holey triangle. We assume that each equilateral triangle of size length K contains at most K holes. With this assumption, we need to show that our Holey triangle has a tiling. For brevity, if a set S of holes in our Holey triangle satisfies our main assumption, that is, each equilateral triangle of size length K contains at most K holes, then we say that S is spread out. For a spread out set S, we say that a triangle of size length K is full of S if it contains exactly K holes. For example, for the spread out set S, in the illustration, the emphasized triangles are full of S. Now, our proof is based on the following lemma. Let S be a set of spread out holes in T. Let T1 and T2 be two full triangles of S, such that they touch each other or intersect. Let T1 plus T2 be the smallest triangle which contains both T1 and T2. Then, T1 plus T2 is also a full triangle of S. Let us prove our lemma and look at the following illustration. To make notation less cumbersome, we denote by T3 the intersection of T1 and T2, and by T4 the sum of T1 and T2. Let T1, T2, T3 and T4 have sizes A, B, C and D, respectively. Now, assume that T1, T2, T3 and T4 have A, B, X and Y holes respectively in S. Since S is spread out, we have that X is smaller or equal to C, and that Y is smaller or equal to D. On the other hand, the geometric configuration of the triangles implies that A plus B is equal to C plus D. Our key observation is that the number of holes in T1 plus the number of holes in T2 is smaller than the number of holes in T3 plus the number of holes in T4. This is simply because T3 together with T4 cover the area which is inside T1 and T2. Thus, we have that A plus B is smaller or equal to X plus Y. From all the inequalities we obtained, we conclude that X is equal to C, and that Y is equal to D. Since Y is equal to D, we have that T4 is full of S, as needed. This proves our lemma. Let us now return again to the necessity part of our proof. Again, we start with a Holey triangle T, where the set S of holes is spread out. Our proof is by induction on the size length n of our Holey triangle. The case n equals 1 is trivial. Hence, we assume that every equilateral triangle T tag, whose size length k, is smaller than n, and where its set of holes S tag is of size k, and is spread out, then T tag has a tilling. Let us denote by B, the bottom row of our Holey triangle, and by T tag the triangle formed by the top n-1 rows. Observe that B contains at least one hole, since otherwise T tag has n holes and thus, S is not spread out. If B has only one hole, then it can be tiled uniquely with diamonds. Also, in this case T tag has n-1 holes which are spread out, and hence, by the induction hypothesis, it also has a tilling. Hence, we assume that the last row B has m holes, where m is greater or equal to 2. Let us denote the holes of B, from left to right, by A1, A2, and so on, until AM. For every 2 adjacent holes in the last row B, we choose an upward unit triangle between these holes, which is found in the row right above B. Let us denote these upward unit triangles by B1, B2, and so on, until BM-1. Now, we cover each BI, and the downward unit triangle below it, with a diamond. In this situation the remaining part of the last row B can be tiled by diamonds. Now, we remove the row B, and the diamonds which cover the BIs, from our Holey triangle. We are left with a triangle of size n-1. This triangle has n-m holes from our previous Holey triangle, and another m-1 holes after removing the diamonds which cover the BIs. Hence, our new triangle has n-1 holes. If these holes are spread out in our new triangle, then by the induction hypothesis it can be tiled, and we can finish our proof. Hence, we need to show that the BIs can be chosen in such a way that the set of holes of our new triangle is spread out. Let us prove that this choice of the BIs is possible. Our method is as follows. We start, by assumption, with a spread out set S of holes. Then, we show how to replace each AI, for I, between 1 and m-1, with a holes bi in the row right above b, such that, at each replacement, we will keep our set of holes spread out. We repeat this process n-1 times, until we produce all the bi's. Since each bi can be defined one at a time, then it is enough to show, for example, how to produce b1. Given the holes, a1 and a2, in the last row b. We will show now how to construct the upward unit triangle, b1. Let sigma be the triangle of maximum size which is full of S, contains the top vertex of A1 and has a base on the line L, which separates the last row B from the rest of our Holey triangle T. The triangle sigma does not touch A2, since otherwise if sigma is of size R, then since it is full of S, it has R holes. Hence, if it does touch A2, then, by extending sigma to the last row, we obtain a triangle of size R plus 1, with at least R plus 2 holes. This is a contradiction to our assumption that our set of holes S is spread out. Let B1 be the upward unit triangle, which has a base on the line L, and which touches the triangle sigma. From our earlier explanation, it follows that B1 must be to the left of A2. Also, B1 cannot be a hole, since otherwise the triangle sigma can be extended to a larger triangle which is full of S. Now, we show that if we replace A1 with B1, then our set of holes is spread out again. To verify this, we only need to check that every triangle which contains B1, but not A1, is not full of S. Indeed, if a triangle with a spread out set of holes does not contain neither A1 or B1, then its set of holes does not change, and hence, it will be spread out after the exchange of A1 with B1. If a triangle P contains A1 and B1, then, after the exchange of A1 with B1, P will have an additional hole at B1. However, this will be compensated with the fact that A1 is not a hole anymore. Hence, the only problem which may arise is that a full triangle P contains B1, but not A1, and then the number of holes in P will be greater than its size. Hence, all is left is to show that the triangle P cannot be a full triangle. We assume that P is a full triangle, and we need to obtain a contradiction. We consider the following two cases. If the base of P is on the line L, then we consider the triangle gamma, which is the smallest triangle which contains the triangles sigma and P. Since P and gamma are full triangles, it follows, by our lemma, that gamma is also a full triangle. But then, gamma is a full triangle on the line L, which contains sigma, which is a contradiction to our assumption that sigma is of maximal size. If the base of the triangle P is on the last row B, then we consider the set of holes S minus A1. Since both P and sigma are full of S minus A1, it follows again, by our lemma, that gamma is full of S minus A1. But then, after adding the hole A1 to gamma, we obtain that gamma has more holes than its size, which is a contradiction to our assumption that S is spread out. Thus, in either way, we obtained a contradiction. This finishes our proof.